So yeah, welcome back everybody. I hope everybody is back. So I'll start slowly in the case that somebody missed out. So this will be the talk on the first talk on the particular module, and so what I'll be presenting now will be based on the grand potential based solvers. So some of you might be hearing this word for the first time. So I will give a brief overview of what this is all about, so that you can also follow the modeling that we are doing with this particular approach and why we chose this this as one of the modules in our software. Okay. Okay, so I'll start with the basic phase field model that we had before. The idea is, as I said in the overview as well, that any phase field model starts with a functional, and the functional has parts with respect to the gradient energy and the potential energy, and the consolidated part, the sum total of these essentially gives rise to the equilibrium interface, and then you have essentially thermodynamic driving forces which tell you how your interface must be moving with respect to the phase transformation that you're addressing. So essentially you will have an equilibrium interface as a result of, okay, by the way, this should be phi. So this is also phi. So you have gradient energy and the potential energy, which is going to give you the balance of these two, as you see over here, gives rise to equilibrium interface, which allows you to map your sharp interface problem into a diffuse interface problem. And the thermodynamic driving force essentially then tells you how your interface will move as a function of time. So you will essentially keep translating, right? So this will be as a function of delta F, and equilibrium is given by this. So that then tells you that once you have a diffuse interface, you no longer need to track this sharp interface that you had before. Rather, you just need to follow the time evolution of this function, and that will give you phase transformation. Okay, so any phase field model that you can write down has two independent parameters, and those two independent parameters you can essentially tailor depending on how you want to control the functional. So one of the ways which is typically useful is to map the two independent parameters into the interfacial energy and the interface width. Okay, so you control these two parameters. There is another way. You don't need to directly control this. You directly control the coefficient of this gradient energy term and the coefficient of this potential energy term, and thereby controlling these two parameters. But a natural choice is to choose the interfacial energy, which is the interface between the alpha and beta phases, which is what this is. The interfacial energy of the alpha beta and the interface width, which is what this is, such that you can better control stuff. So the idea is precisely to take these two as the input parameters, because one controls the material property, other controls the resolution that you will be choosing for your interface. Okay. But this is not generic. You can choose, as I said, any other two independent parameters which will effectively control this, but you can choose that as well. So now, so essentially, this gives the equilibrium and this gives the driving force. So let's see how you can give a driving force to the phase field model that allows it to move. So one of the simplest ways is essentially to couple a thermal field which evolves with time, and that is essentially solidification of a pure material, and that can be done that can be used for incorporating a driving force to the problem. And the way one would do this is essentially modify your functional by putting a driving force, which is delta F, Fs minus Fl, and which is the driving force in the problem, and then you multiply it with an interpolation function such that the driving force essentially manifests itself only in the interface. So you don't need to worry about these evolution equations, but just to take note that you have required an evolution equation for the order parameter, which is tracking the solid liquid interface, which is the function that I just showed you now. So time evolution of that function will be treated by this, and you need an evolution equation to follow the macroscopic temperature field, which is going to control the driving force, which is sitting over here. So pictorially, if you were to draw the free energy versus temperature of the solid and the liquid, you see that at Tm you have no driving force, which is the melting point. But as you are depressed from Tm, you have a difference between the liquid and the solid free energies, where the liquid has a higher free energy, giving you a driving force that will essentially move your interface, as I have just shown, in the direction. Okay. So that's a simple way that you can put in driving force. That is essentially incorporate the thermodynamics of the system that you are trying to model. And once you have put the thermodynamics, you will be able to put in the driving forces in the model and thereby go forward. Okay. So now let's say we want to generalize this for an alloy, which is in general a multi-component alloy. But let's start with a binary alloy, and we ask the same question: how do we write this driving force as? And that will bring us to the grand potential model that we are trying to write down. And so the way to find out what is the driving force one needs to input for appropriating this solidification problem for an alloy. There are many ways in literature that have been there. So there are models of type 1, which are written in a particular problem. But without going into too much details, I will tell you that these models are not in too much use now because of known problems. I will not go into details of those problems, but it is just tell you that these models of type 1, which are written over here, are no longer in use in typical commercial software or even in literature for any realistic purposes. What are used are this type of models, which are type 2 models, which are the KKS type of model, or the what are also known as the Steinbach-Eichen model or the Thiaden model. So by the way, this is the same person. This is just a change of surname, but these are the same models written at different times, and these are sort of to give you a historical perspective. These two models were proposed almost at the same time, and mostly in a discussion amongst themselves, but they came out with two different models, and essentially they share the same spirit. And so this is class of type 2. And then there is a model of type 3, which are the Folch-Plapp-Echeverria models, where you essentially manipulate the free energy in a way such that you are able to take care of these problems that are there in model 1, and thereby accordingly write down functionals which are giving you the right coupling with the thermodynamics. Okay, so this is also in use, except that the limitation is that to generalize this stuff for any alloy becomes very difficult task, particularly because because of the things they do to the functional, which are very tailored for dilute alloy approximations. So the generic thing is what we look for are stuff which are more generic, and that's where we came to the grand potential. And this is some work that it is based on work that is listed over here and here, where the idea is precisely to generalize the driving forces such that you can treat any alloy under consideration, both multi-component or binary as it may be. And the idea stems from the use of the grand potential, which is the well-defined thermodynamic potential. That is, it is the Legendre transform of the free energy, which is typically the Helmholtz free energy. And you basically take the transform of the Legendre of this free energy to derive what is known as the grand potential, which has naturally a state variable, which is not the composition anymore, but essentially the effective chemical potential, which is the slope of this line. Okay, so this is the effective chemical potential, not the true chemical potential, and this effective chemical potential is the variable on which the grand potential is dependent on. Okay. Okay, so this is what we will be using as our potential, and the reason for using this potential is well detailed out in these literature. It essentially takes care of these problems that are there in Model 1 and generalizes the concepts that are there in these in an effective manner, such that both memory utilization as well as code implementation becomes much more generic and simpler. Okay. All right, so the motivation for doing this is, I will show this pictorially so that you can appreciate this. So suppose you have an equilibrium between solid and liquid. So you have the solid and the liquid free energy curves, and the equilibrium between them is given by this common tangent construction, which is giving you the points on the phase diagram corresponding to this line. Okay, so this is a CS and CL. Now, the same information, if you were to plot using the grand potentials, you would essentially get the grand potential, which is this value. This, if you were to plot this as a function of the variation in the slope of this line of the tangent, as the composition varies, you would get lines like this, where you essentially have equilibrium at the common tangent given by this value when both the grand potentials are equal for a unique value of the slope given by the mu equilibrium. Okay, and this, if you compare it, is in direct relation or directly analogous to what you saw for the pure material case, where you essentially have the melting point over here as the point at which equilibrium, and anything lesser than this, you will have driving force where the grand potentials are no longer equal, and similar to what you have for the below melting point, a driving force existing. So that is what is shown over here. That means as you deviate from this chemical potential, effective chemical potential, you start to have a driving force, just like you had for the pure material case, where you started to have, for a given undercooling, a driving force in the problem. Okay, so in some sense, the direct generalization of the pure material problem is to this problem. So a direct generalization exists, and that's why this becomes a natural choice for us when we want to extend the formulations to alloys in the problem. Okay. So the point is, therefore, you start from the what is known as a grand potential, where the grand potential density sits over here. The same two terms in the functional sit over here, which is the gradient and the potential, giving rise to an interface. But then all the thermodynamics goes over here, and as I showed you now, the generalized thermodynamic potential or the grand potential densities for a general multi-component system can be written down like this, and all of this can be found out in these two papers quite in a detailed fashion. Particularly for multi-component alloys, you can find a nice description in this paper and get all the details there. Okay, but the basic idea is what I had just detailed in a pictorial fashion, and therefore this is something that you can take away from this. So and the similarity can also be seen in terms of just writing down for a simple binary alloy. If you were to write down in the simplest form the evolution equations for the phase transformation, which is, as I said, that function which is going to evolve as a function of time, phi as a function of t. If you were to write it in its simplest form, this is the one that gives you comes from the gradient and the potential terms, which gives you an equilibrium interface. And this is the driving force that makes you drive the interface. And you see over here, this term over here, it directly something that is very similar to the T minus Tm term that you had in the case of pure materials, Lt minus Tm into h of phi. This is what would come in a pure material. And in some sense, as I said, the temperature and the chemical potential share a nice analog, and thereby you are able to directly see the extrapolation from a pure material case. And because this is a dynamic variable now, you have to transform your mass conservation equation from the composition to a chemical potential, which is easy to do. It is just a reformulation, just like you solve for the temperature in the case instead of the internal energy in the case of the pure material. So that's the same analogous transformation, and one can see this quite readily. And the more generic form can be written down over here, where you take in the for a generic interface gradient energy and a potential, and the grand potential density, one can write down for a multi-phase formulation. I don't want you to, I don't expect any of you to basically understand everything, but except that you can take that there is a generalization available for multi-phase, multi-component stuff, which is written over here. And anybody who is wanting to explore it further, the publications are existing there. Okay, so I will not spend too much time here in that sense. What it allows you to do for such a formulation is that it allows the direct computation, direct coupling to databases, as long as open databases are available, or even if some information from the databases is available. And the idea is there is two ways to couple it. One is the direct computation of the driving force from CalFAT databases, which is can be done using interfaces like PyCalFAT, which are open, as long as an OpenDTV database is available, or you construct approximate free energies wherever you do not have open databases, and thereby you can construct these simpler forms which are parabolic in nature, which can easily be extended to multi-component systems as well. So the description of this is also possible, and you can find it in this particular literature over here. Okay, so that's essentially telling you what all we can do, what the model is based on. And now what I will essentially do, okay, just to complete the stuff, there are other things that one must write down when you write a quantitative phase field model. It is to take care of some of the defects that come because of the use of a diffuse interface, which is much larger than the atomic interface width that is typically in materials. And the reason you use such large interface widths is because you want to treat microstructure evolution of large structures like dendrites, okay, which are much larger than the resolution that you have for the the resolution of a real atomic or physical interface. So because of that, you will obviously have to take care of certain effects. So people who are unaware about this, it's okay if you do not understand this. Except that people who are aware, please, it is for them to note that these corrections are there as part of the model that we are sharing and the code that we are sharing, and they are already part of the model in terms of the anti-trapping current and the choice of the what the relaxation coefficient have to be, and the details of whoever is interested in how such corrections at the interface are taken care of in typical phase field models, such that thin interface defects are not part of the model, can be found again in this paper. Okay. Good. So that's what we can. This is all the description I wanted to give. In terms of the model description, and what I will now do briefly is to give you in the 3-4 slides is to give you a brief description of what are the particular forms of energy that we are using, and then go to the exact demo, to the demo of the solver. Okay. So the free energies, there are essentially chosen in the solver using a key in the solver, which is function f. And we will be inputting more number of functions that are possible, but presently one solver exists, and this is sort of already generic enough because it allows you to treat different free energies and different systems in an approximate fashion. And I'll tell you that's all the approximation that you need for any given system, particularly for phase transformations, is because if you write a generic parabolic free energy of a multi-component system in this manner, the curvatures of the free energy can be directly extrapolated from the from the thermodynamic databases, and these constants that exist in the parabolic coefficients can be approximated, can be estimated from the equilibrium compositions, which can be again derived from the databases. So in some sense, most of the stuff that is already part of the thermodynamic databases in terms of the thermodynamics can be included into a simplistic free energy of this form. Why is this already sufficient? It is because most of the things that relate the interfacial evolution to the local thermodynamic equilibrium at the interface is directly controlled by what is known as the Gibbs-Thompson coefficient, and the Gibbs-Thompson coefficient at leading order is just dependent on this. So for most microstructures which are much larger than the capillary length, you are actually going to be just dictated by this particular term. And if you get this right, that is right as per what is the most right available in literature, which is the thermodynamic database, you will almost get the evolution correct. Okay, so if you get the compositions and the free curvatures of the free energies correctly, you will essentially get the dynamics correct, and thereby this function is already generic enough to treat most systems of our choice. How do we treat temperature dependence? Where the temperature dependence is again a local linearization about a temperature of choice. So you have C equilibrium and C equilibrium solid and C equilibrium liquid, and you use the slopes of the liquidus and the solidus in the local space that you have chosen, and the system will be linearized about that. So essentially, for extrapolations about a given choice in the phase diagram, you can already get temperature dependence by taking in the slopes as an input, which is taken in the solvent. And this idea can essentially be extrapolated to multi-component systems as long as you can extrapolate the multi-component liquidus and solidus slopes from the thermodynamic databases, which is typically a system thing that you can output in your typical thermodynamic calculations that you can access in thermocalc or anything. So in some sense, most of these stuff that are required by the solver can be derived from thermodynamic databases quite readily, and thereby you can directly interface with your with the solver for a generic alloy. Coming to the potentials, which is the W term, as I had just said, A plus W gives the interfacial energy. So we have just completed the delta F part. So we will now come to the W, and this W is something that there are two possibilities that exist in the solver. One is the multi-obstacle potential, which gives you a finite interface between into 2 points between 0 and 1, and this is of a particular type. So this is a sharp potential. And this is particularly useful for doing, computationally efficient simulations, because your gradient is restricted to a very finite region in space, and therefore you need to basically intensively solve only in a finite region. This is in contrast to the multi-well, because in the multi-well region, the gradient is you only reach asymptotically to 0 and 1. And thereby there is a finite gradient that exists in most places, and therefore the computation is compared to this is more expensive. But both choices are available in the solver, and they can be accessed in the in file using this. And as I have just said, you can actually write down your own functions and function W function if you don't like these, and you can write down your own potentials and functions. There is the way to do this is something like write separate header file and including in the solver. So when we have a separate developer version workshop, I will show that explicitly. And the number of steps you actually need to do that is very, very small. You just need a separate key in the in file that you need to include, as well as a separate header file that you need to include. And the number of steps are actually limited to just 3 or 4, which makes it highly ideal for anybody who wants to write down a separate function of their own. So these instructions we will be posting on the document and the manual in due course as we develop along. Coming to the last term, so we have completed A, W, and delta F. So we have completed delta, and the last term is the gradient energy. Here is where typically we use a multi-phase for formulation of the gradient energy using what is known as a Q vector. So this is a particular choice which allows us to treat each alpha beta interface separately in terms of what properties we want to attribute to that interface. So for example, if you have a 3-phase microstructure, let's say you have alpha, beta, gamma, and you want to attribute a particular interfacial energy to this and a particular interfacial energy to this and this to this, you can choose each interfacial energy differently using such a formulation. Not only that, because it's this function is interface specific, you can actually attribute anisotropies which are independent of each interface. So for example, you can make this interface anisotropic while this interface remains isotropic, and so on. So you can independently control the properties of each interface through such a formulation. And this is you can also find it in the Nestler publication that I just shared with you, and it allows you to do that. You can also give anisotropies which are written over here. You can impart separate anisotropies which are written through this function AC, which is a function which is over here. And the anisotropies are typically taken in what are known as this polynomial forms of the interface interface normal vector. And so this is a fourfold anisotropy, but again, as I said, you can choose your own anisotropy functions through this choice, which is function anisotropy in the in file. This is the anisotropy type in the in file. So you can choose anisotropy type and choose the particular form of anisotropy for symmetry of the anisotropy that you want. So for 4, it will come to this. We will be coding in more forms, so that's why this number is static for them. And you can again, this is something that a user can develop by himself and write his own anisotropy function. And again, how to do that is something that we will share in due course in our manuals. Okay. Okay, so finally, the last term in the equation is tau dou phi by dou t is equal to, so something was there over here in the evolution equation. So the last term is with respect to the relaxation coefficient. All other terms have been taken care of. So the tau this is the relaxation constant for the particular interface that you are talking about. And again, we have flexibility to give relaxation constants with respect to every interface separately. So you have tau alpha beta, which is similar to the gamma alpha beta that I just said, where you can give different interfacial energies to each interface, but you can also give different relaxation coefficients to each of the interfaces, and thereby you can give this value as well. Okay, so this is again controlled by the tau key in the in file that you have. Okay, so that's all with respect to the description of the solver, and now we will quickly go through a live demo of how the solver functions, and that will give you a better idea of what we are doing. Right. Okay, so let's go there. So I have MicroSim already installed. What I will do is to go there. Just 1 second. So, okay. Cool. All right, so cd MicroSim, and there's a Python thing over here. I will run it directly through the interface, so that for you guys there will be the logo you can directly download from the So there's a nice logo that comes in the software sections of your Ubuntu. You directly click on that, this interface will directly open up. Okay. So now what I will do is first to show you a simple example where I will just import in files which are already there, and I will make changes in them and run you through those changes. All right. So we are talking about the grand potential. So I will choose this. So I will choose this in file. So I can choose this in file by going to the respective directly. I have made some in files for this discussion. So I will choose, for example, input.in. Okay. So I will run you through them. So you have the simulation geometry, which comes about depending on what grid I have chosen. You can go through the number of phases. So if you see the phase names which are read from the in file, alpha and beta, if you want, you can change them. But the properties will require changing as well. So if you want to keep properties same, it's better not to change these names that have been coming in. Then this is similar to the component names. You can give your component names. And then you can directly go to information that is relevant to how you run the software. So for example, we are doing short runs here. So we will just give small times so that we can do several things. We are doing a new simulation, so we are not restarting. So this should be 0. So you see the parameters are already read in. So I am using a diffusivity matrix, which is so this is a binary alloy. So there's only one diffusivity, interdiffusivity, that you have to take care. So in the alpha, it is a solid phase, and beta is the liquid phase. So only beta has 1 because these are non-dimensional parameters. So we will work with that right now. So alpha is 0 and beta is 1. Essentially implies that beta is because beta is liquid, you have diffusivity only in the liquid phase, right? Then you have the interfacial energy, which is again just for discussion purposes 1, and R and V are sort of constants. If you write realistic free energies, these constants will be used. And then you give boundary conditions. Presently, I'm using Neumann boundary conditions for all. If you want to change, you can just click on it and change it, right? So for example, you can click on this. It will show up which boundary you're talking about, right? And change it if you want. Presently, I'll choose NBC itself. Right. So for example, here it lights up the boundary and you can choose it. And so on. So, and this you can do it for every field separately and run it. Right. Good. So now we come to domain filling, and we are going to fill our domain with a circular precipitate at the center. So what you can do is to click a cylinder, and I want to fill in a phase alpha. Okay, so I'll fill alpha. And I add a cylinder. So we want to put it at the center of the box. So the box size is 100 cross 100. So the center of the box would be 50, and I can give a radius, which is some radius, which is 10. And this radius is in terms of grid points. I can save this information. It writes something to in this form, and it will essentially write it to a file. Okay. If I don't like something, I can also go and do edit of this. I can do edit and I can do update, and it'll save it. If I don't want to, if I write several of these, it will just do one by one. So you can do multiple cylinders at different positions in the domain. It will just work, right? And you can, and by definition, what we do is, and the definition what we do is that all of these what you call all these filling, the filling of, if you have multiple phases, you just need to give filling information about the first n-1 phases. If there are n phases, the rest of the domain gets filled by the liquid phase, by the last phase in the list that you have. All right. So that's why I'm filling only alpha. The rest of the domain gets filled by the last phase automatically. All right. Very good. So if that is so, then you can just forward, and then you just come down to this, where you now input model specific parameters. And presently we are doing binary simulation. So we are using a flag, which is the optimizer for doing binary simulations. Similarly, there will be flags for doing ternary and dilute simulations. If you don't use any of these flags presently, what it will happen is that you will essentially run the entire multi-component solver, which involves a matrix inversion, and that might be slightly slower. Okay, so it's good to use, particularly for binary and ternary simulation, these flags, which will be fastening the simulation. Write HDF5 is a key which will be only useful if you run a MPI solver. For us, it doesn't make any sense, so we'll put it to 0, right? And track progress is essentially after how many time steps it will be running your output to the file. And these are parameters, as I just explained in the model. You can find a description about them in the manual about what these are. As I just said, function anisotropy equal to 1 implies that you have anisotropy kicking in. So presently, I'll give you a first simulation where it is turned off. So I will put it as 0. So if it's 0, this parameter doesn't kick in, and the strength of anisotropy, which is written over here, also doesn't kick in. All right. And this is a potential function. Again, you have to give these terms. Function f, which is the interface, which is the free energy function, which I just talked about. And there's the equilibrium temperature, filling temperature, and these are which. So this is important for us. It is essentially telling us these are temperatures about which you are linearizing your system, and T is equal to 0.97 essentially means you're giving some undercooling for the system. All right. And noise is for giving noise at the interface such that you can do simulations for them, right? So, so this is the thermodynamics. I will not go through the detail, except I'll show you quickly what the simulation does. So you can now go to the filling input test, and I will name it as input ISO, and ISO.in, and it will generate files. It will tell you where to generate files, and there's generate files. I have made a folder, so it's a good idea to make a folder where you will be writing down. So I will just pull my folder here, and I will generate files. Okay, and it generates. And now this is okay. This is already done. So okay, right. So let's choose them. Okay. And then you can choose the output file. Output. I will name it ISO, where you can run, and then what you can immediately do is to run the solver, and it will open a separate terminal where something will be running. All right, and this will run for some time. It will take about a minute to run.
This is Gerald here.
Gerald, yeah.
Yeah, I just wanted to know, in order for us to run this solver, should we be on top of this grand potential model? Or
no,
is
you can choose different models. You can choose different models. Okay, and this is just one module in the solver.
No, what I'm asking is that the model parameters and the various other things.
So when you choose a particular model, the section over here, model parameters, will be specific to that model. So let's say you choose.
So will the model parameters be auto-filled, or we need to?
So there are already some example in files. There are some example in files. So you can just import, as I just imported here, you can import them and they will autofill. Okay. And then you can modify, or you can modify based on that, right? So.
Okay.
So now you can preview in ParaView. So it will open a terminal for previewing in ParaView. It takes a bit of time the first time. So. Okay. And what you see is that everything has melted away. And this you can see from over here. This is all the outputs that you generated, and what you see is that you can show a movie and you see that it is gone away. And people who are in the phase field literature will know that this is because the temperature is not appropriate, right? So if the temperature is not appropriate, because temperature is not appropriate means it's lower than the Gibbs-Thomson undercooling. Therefore, one needs to, for growth, you will need to change the temperature. And so that can be just quickly done over here by changing the parameters, where you input the temperature, and now we'll make it 0.94. And I can quickly do the same thing, generate the files in the same place, create the in file, and then I run. Okay. It's a good idea to close the terminal when you are already finished with learning. For our next problems, we will just reduce the number of times it needs to run so that we can do quicker and play around a little bit more. Okay, so we are almost there. Just a few more seconds. And so this interface is essentially useful for you to get your in files ready. And once your in file is ready, typically you take this in file and the so presently I'm using just the serial solvers. I'm not using the MPI as well. So, but when you do the in files are generated, the solvers are already part of the installation in the home directory. So you can just make the solver there and take the executable and the in file to the cluster where you want to run and execute it there. In future, we will also be writing down or giving you scripts for running on specific NSM machines, such that you don't need to figure out or worry about how to run your code on a particular NSM machine as well. So, but this is going to be in the future releases that we are going to have. So again, we'll do preview in ParaView, and so you can now check. Now it's grown, and it is essentially you can see that it is growing by just taking this, and so you can just shut this off and run this as a movie. You can see it's starting to grow, and that's because now the undercooling is enough to take care of the Gibbs-Thomson effect, and it's beyond that, so that growth can happen. Previously, you were below the critical undercooling. Okay, good. So that's the simplest case. And then what we want to do is, let's say I want to put anisotropy into the system. So what I will do is I will just go to my model parameters. Potential model. I will go here, and I will just put function anisotropy as 1. And presently only anisotropy for type 4 is loaded, which is the 4-fold anisotropy. So I will just use this presently, and the strength of anisotropy of only one interface, because we are just having solid liquid interface only. So that's one strength of anisotropy is there. And just in the interest of time, I will run only 5,000 steps so that I can write down things quickly. So filling same, model parameter is the same, and then can directly go to generating files, and I will name this separately. So MISO and I'll generating files. So I'll choose this generate, and I will give a separate name. So then I'll run. Okay.
Abhik, as we are saving it at regular intervals, right?
Right.
So as the simulation is running, will we be able to visualize them?
Yeah. So that's what. So I'm presently previewing in ParaView, but that data is written in that folder. So if you just go to that folder where it is written down, you can just open ParaView there and then run. Yeah.
Okay.
This is for just, as I said, this interface is for checking your stuff is going on correctly or not. So, and that's what this is all about. Because there are several things with respect to different models. This gives you a nice interface to get along with each model separately. Yeah.
Okay.
So I think it will go to 5. Good. So we can do preview and ParaView. And, apply. So now you see it takes an isotropic shape over here. And if you want to see the progress of the simulation, you can just open the most recent one. And you can open all of them together, comment this out and apply. And yeah, so you see it's now an isotropic shape of a given orientation. And now we'll play around this a little bit more. What we will do is we will rotate this anisotropy such that let's say your crystal grain is rotated by some amount, right? It's not exactly oriented like this. So you would like to give a rotation, right? So we can do that quite readily. So we can again go to the model selection. Next, that's there. And here is where you have this thing which is telling you the Euler angles with respect to x, y, z. Since it's a 2D rotation, 2D simulation, only rotation about z makes sense. And what we will do is to tell rotation about z with the angle of 45. So we'll rotate by 45 degrees. Okay, and that's what we'll then finish this and run the simulation again, where we'll give this a separate name. We'll give this rot. Rot and generating files. Rot, and then you can just run.
Abhik, there is a raised hand.
Yes, I can't see any raised hand. What is the any question? Any questions? You just directly tell so that I can, because I can't see the hands here.
Yeah, some Purnima has raised hand, but I don't know if it was by mistake.
Purnima, you can directly address your question while the simulation is running. I can answer it. Yeah. Yes, Purnima. Or you can just type your question in the chat and somebody can read it. That's also fine.
There is one question from Harris Daniel in the chat.
Right.
How are you coming up with non-dimensional model parameters?
Okay, so non-dimensionalization is part of it's the user's headache. So if you put in non-dimensionalized parameters, the code will run with non-dimensionalized parameters. If you put in dimensional parameters, all things will run with dimensional. So the infile does not know any non-dimensionality. It is whatever parameters you input, the evolution equations are agnostic to any dimensionality. So it's the dimension that you start with. So if you give non-dimensional, it will run with dimensional. I chose non-dimensional because I have already non-dimensionalized my system using some scheme of choosing length, time, and energy scales. And once I have done that, my infile is non-dimensional. So whatever you're seeing is non-dimensional. All right. But you can as well put in dimensional parameters and it will run. No problem. Okay, so we can now check. You see now the anisotropy is such that you are rotated by 45 degrees. So previously you were a diamond, now you are a square. Okay, and then you can also see how it is evolving. Rotate, and you can just quickly check how it is evolving, and you see it's evolving properly. Right. Good. So that's what you can do with a single phase. And now you might ask, OK, I can do one with single phase. Can we do all of this in with multiple phases? And yes, you can do. And the easiest way to do that is basically to import a separate infile. So what we will do is we will just separate import of infile, which is because there are when you put multiple phases, the sizes of the matrices and everything changes. So you can just choose an infile, which is I have already made. And you can read in the simulations as there's somebody's mic who is unmuted. Can you just mute it? Yeah, okay. So you can read in the infile like we did for the single phase. And so you can go through now. Their number of phases are 3. So I want to do a multi-dendrite simulation where one of the orientations is one value, another orientation is a different value. All right. And I'll still do a binary simulation. And again, just for time's sake, I will do a short iteration. So that I can do this and we'll keep all properties other than the same. Boundary conditions we will not change, except we will change the filling. Okay, so now we have 2 phases, 2 solid phases and 1 liquid phase. So we will just fill it appropriately. So we'll fit 2 cylinders, one at the center. Let's say center phase is beta. Okay, and beta phase has a center which is 50, 50, and radius is 10. Okay, and then I'll fill in the alpha phase at cylinder alpha, and I will fill in this at 0, 0, and this is at the same radius, for example. So invalid center point because this. So it will give you throw up error messages as well, which is nice for somebody who is doing a mistake. So what it does is essentially it fills up one phase at the center, which is 1, and one phase at the one corner of the phase of the system. All right, and each is of size 10. And we can then go to model specific parameters. Okay, well, I will see the temperature we are using here so that we make sense. Yeah, using the same temperature, so fine. And here we will say multiphase in. Multiphase.in, and what you will see is that you will generate files. So let's generate. Oh, it was the right folder. Sorry. So yeah, this is the tutorial. So choose here. Right, and then we can make this multiphase. Note out, and then you can run in the same way. Yes, Abhinav, just ask your question. Abhinav,
I wanted to ask. Yes,
yeah.
I wanted to ask, are there provisions for running batch processing, like multiple simulation runs with different parameters, automating the task?
Right, so that is up to a script, no? So essentially you can write a script, call the thing once your infile is ready. This is essentially for the interface for running, generating your infile. Once your infile is generated, you can basically write a script for doing those batch processing. That's a good suggestion. We will try to put in some scripts ready for use so that you can immediately batch process certain parameter changes. We will provide them along, but that is going to be irrespective. I mean, separate to the infile integrator, because the infile integrator, the main motive is to basically allowing an interface where you can generate your infiles quite readily, check them before you run a big run. That's essentially the idea, right?
All right, thank you.
Yeah. There was one more question, I think.
It is from Krishnendu Mukherjee.
Yes, Krishnendu.
Yeah, shall I read it out?
Yeah, you can read it. Yeah.
In case of austenite to ferrite transformation in steel,
right.
There is an increase in volume. Can you take this
increase in volume is presently not part of the solver as yet. That's a research problem again. So things that are parts of research problems will require model formulations and so on. They will be done in the future. There are existing models where people try to do it, but those are not the only models. So they have to be model formulation problems. We will be investing some time once this software is essentially released with all the know-how until now. So that's essentially what the idea is. But that is certainly a good question, and we will attempt to address that as and when we have research money for doing that thing. Yeah, essentially that is the issue. Okay, so let's apply. Okay, so I will just show you what is, I'll show you the liquid. So now you have two phases. One is rotated in the normal diamond shape and one is rotated 45 degrees as you had promised, and you can essentially follow the evolution again. So for example, this is multiphase, and can close this, can open this, and yeah, so, and you can follow it in the liquid because both phases are approachable. So you can see both of them are growing, one with an anisotropy which is slightly rotated. So there are two phases now. So a multi-phase problem is something that you can solve for. All right. So finally, I wanted to also show you, in the interest of time, I'll just show you one more example in what you can do. So this is a multi-phase, but not multi, chemically different phases. So I'll essentially, as a last example, show you a multi-chemical phase problem where the two phases are essentially different phases in the real sense, not just crystallography. So that we will address again by choosing an infile which is already there. So you can choose here. So I'm going to grow in a particular direction. That's why you see elongation of a domain. And again, because we are doing small simulations just to show you the idea, I will just reduce the direction at once. So the phases are all there. So I will not go through them.
Abhik, I don't know if you already answered, but somebody
Right.
is asking about initial nuclei overlap.
That can be done. So initial nuclei, it's up to you. So if you want to do initial overlap, you can give them.
Yeah.
It's about the filling. So
yeah,
you can.
The question says what happens if the initial nuclei provider overlap or touch each other?
It doesn't really matter. It just overfills. I'll just show you if you do that. Well, not in this case. In the other case, I will just show. Okay, in this case also it will overlap. So, so let's go here. Diffusivity. Beta is there. Only liquid is there. Diffusivity. So you have three phases: alpha, beta, and liquid. And there are three interfacial energies. I have chosen periodic boundary conditions in this direction and Neumann boundary conditions in the growth direction, which is this. So if you choose Y, so the Neumann boundary conditions in that direction, Y plus, and Neumann boundary conditions in the bottom, whereas X plus, which is this is periodic boundary condition, Y plus is, sorry, not Y plus, X plus is again periodic boundary condition. Okay, so two periodic and two, and this is true for all the fields that I have chosen. So we'll do that. And here is where you can, so if you overlap, for example, let's say you fill alpha first and the second phase is, so these are sequential filling operations. So let's say you fill up phase 1 and after that you fill up phase 2 such that it overlaps. It will just overwrite the region where beta is there and you have alpha there. Okay. So it's simple, similar to a flood fill algorithm. So it will just overfill the sequential filling is done in a sequential manner. So first phase is filled first. When you fill this, any overlapping region is filled with this phase, erasing the other phase. That's all. Okay. All right. So now we will fill something which is with respect to our system. So what we will do is first we will delete these guys. And we will fill cubes of alpha and beta placed at the bottom. Okay, so what we will do is 0, 0, 0. Okay, and I will give this size is 2850. So I will fill half the domain with alpha and half the domain with beta. So 25, and I'll give a small height in the y direction so that you are filling 25 length and 10 in the height. Okay, so that's alpha, and then I will fill beta. And this is done again. This is starting from where alpha left off. So 25, 0. And the beta is 50, 10, 0. Okay. So you filled up 0 and 1. These are cubes now, not cylinders. And all you have to do now is to, I will write down eutectic. And .in, and I will generate in files, and I will generate them at the place I have been generating them. So good. And this is eutectic. Eutectic.out. Yeah. And then I will run. Okay. Yeah. So any questions you can ask when the simulations are running? Anybody who has questions just can.
Maybe it's a repetitive question, Abhik, someone would have asked.
Right.
Just wanted to know whether for each phase we can plug in individual orientations. I think
you can do that. That's what I did. That's what I did.
Yeah, okay.
So basically, you can choose for each phase, you can give different rotation of the anisotropy.
Okay.
That's what I showed in that multi-phase simulation. That's what the idea was.
Yeah, I missed it.
Yeah.
Thanks.
Okay, very good. So we can preview this. Let's see if we filled in everything correctly or we did some mistake. And you see, you have alpha, beta, and you see them in the liquid, right? And what you can do is to check the evolution again. Eutectic. And we'll just shut this guy out and this. Okay, let's follow that in the liquid. So we're doing a very short simulation, but you can see that it is growing in the direction here. Okay, so right. Okay, so that's a eutectic, and then so the only thing now I want to show you, so we can do multi-phase, multi-component, multi-chemical phase, and now the only thing is multi-component is what I want to show you. And for that I will not run it because of the paucity of time, but I will just import a in file and I'll show you how the parameters look. So I will go back, import a in file, and choose an in file over here. Not here, sorry. I'll choose an in file, and it's all the similar system, so I can generate in files. So the number of phases are 4, number of components 3. You can choose iterations and parameters in the same way and choose parameters. So diffusivity now, because it's a multi-component system, it's a ternary alloy. You have the diagonal the diffusivity matrix is now having 2 components over here. Okay, and we are choosing a diagonal matrix here. But if you choose a full matrix where your non-diagonal elements are there, you can also do that. Okay, so there's a possibility to choose both full and diagonal matrices. Diagonal matrices allows you to fill lesser quantities. That's all. And gamma, each interface, again, there are now 6 interfaces, so each interface can be filled with different properties. Boundary conditions can be given in the same manner. You can fill it up. Now you can fill up 3 phases as you can fill up. You have to just do the calculation and fill it up as I have done, and you can generate the in file. Okay. So I will not do that. I will just, because we are short of time, what we will do is just show you what the simulation would look like in the solver, because I have already done it and done that, and I have saved it somewhere. So I will show this already. So this is how the simulation would look. So this is a 3-phase, 3-component eutectic alloy. 3 solid phases, 4 phases, 3 solid phases, 1 liquid phase, and 3 components going into the liquid, right? Right. So yeah, that's what it is. So you can do several of these type of simulations, and yeah, so that's essentially. So we are already in 1 hour. So I have actually.
Can I ask a quick question?
Yeah, so essentially I will close my talk now, and then we can
sure.
do this. Right, so let's leave it over here so that there's nothing running. Yeah, please go ahead.
as of now, chemical reactions are not there, right? Between components.
No, chemical reactions. Okay, chemical reactions are something that are not there in traditional phase field models. So,
Okay.
but chemical reactions, in principle, if you are having chemical reactions in the bulk, these will be mass balance equations which can be incorporated. Okay. These are additional modules which can be. I mean, these can be put into the the mass conservation equations where you have a source term for the chemical reactions. So that can be incorporated as a special flag in the module. That's not an issue.
I see. Okay, got you. Thank you.
Abhik, there is another question, Dr.
Right.
Sai. Can this be used for 2D models, for example, simulating growth of crystalline films while varying substrate?
Yeah, so there is where, so you would have, in principle, you can do it, but if you want to include stresses, in the present grand potential model, stresses is not included. That means epitaxial stresses, but we will be including them in the future releases. But you will already see a version that is from Dr. Shashwato, where you will see that elastic stresses can be included, but we will have that as part of our releases in the future, where we will be taking stress effects into account while the growth on a substrate, for example. Sai, Dr. Sai, does that answer your question, or?
Oh yes, thank you very much.
Okay. Okay, very good. So questions, and we can. So that's the end of my talk. So essentially, I just wanted to show you all the capabilities that are presently possible, and I have already showed you the large-scale simulations that were done on the NSM machine using the same solver. So just to give you where the solvers are. So if you go to Google, you can go to that's the first hit in the Google. So you can see our repository here. And in this repository, if you choose this MicroSim_lab, this will essentially load up the interface that I just showed you. You can just follow the installation instructions that are there, that are there already in there. And the solvers are separately also there. You can download them, and they have different manuals for each of them, showing describing the model, the model parameters, how the implementation is done, and all of that. So as and when you want to download, you can do that. All right. So yeah, that's what I wanted to share.
I just have one more question, if that's okay.
Narasimhan, yeah, Narasimhan, yes, go ahead.
Yeah. What sort of errors does it throw? Like if you do something wrong.
Are the computing resources of the? I mean, you are running on multiple cores, right? So
presently,
is that available for everyone? Or
that code is also there. So I'll just,
okay,
there are two questions. That's two things. Let me just answer Shriman's question quickly. So Shriman, you see this code now, MPI code. This is for multiple cores operation. So if you download this code, compile it, and take the executable to and the infile to the follow the instructions and run it on the multiple cores, it will just run. So for example, this was the code that was used for the 19,000 CPU core run on the NSM. Shriman?
Yes, sir.
Does that answer your question? Or?
Yes, sir. Yes, sir.
Okay. Yeah, Narasimhan, yeah, go ahead with your question. What did
I just wanted to know, suppose we did something wrong. Are there errors that this will throw?
Yes. So for example, when you fill wrongly, it will throw up error messages. It will tell you have not filled up enough parameters for the particular consideration. So it has fallback checks.
Okay.
That's why this interface is important, because that tells you to fill the infile correctly. It helps you that way.
Okay, sounds good. Thank you.
Yeah. Questions? There are more questions, I think, coming up. One more. How are nucleation events happening? Okay, nucleation events are presently handled by hand. So as you know, phase field models are not meant for nucleation, but per se, but we will be having a noise defined nucleation. I mean, stochastic noise stochastic noise imparted nucleation in the future. Not in this release, but we will be releasing in the future thing. Yeah.
Sir, one more question.
Right.
Are the multi-grain models also in your pipeline?
The multi-grain is already there, no? So grain growth, you mean?
Yes, sir. Multi-grain.
Yeah.
phase
The next step. So the solver as such can already be used for grain growth, except that we don't have the optimization for locally reduced order parameters. So it will run a bit slow, but it will run. So in the future releases, we will be putting in the locally reduced order parameter optimization, which will essentially allow you to run that with both memory efficiency as well as speed.
Okay.
Right. So also there are other multiple branches of development going on using the orientation field models. We are also doing implementations in OpenFOAM. So we will also be porting that in the multiphysics solvers. Yes, any more questions? Okay, so if that's not the case, in the interest of time, I will end my presentation and we'll have a short lunch break because we are supposed to be having lunch, and so around 1:30 is something that we can come back. Everybody agrees? So.
Yeah, we set a time and tell the current time, so everybody knows.
Yeah.
Relatively, what is the duration?
Right. So 1:30. Let's decide at 1:30.
And the time now for you
is 12:56. So
good, fine. Okay, exactly half an hour from now, we all show up, but we can just leave the meeting as it is.
Right.
Yeah.
Exactly.
Okay. Yeah.
Okay.
You want to pause? You want to pause the recording or?
Yeah, I'll pause the recording because otherwise it will increase our work.
Also, we have to
do fill that up.
Yeah, we can ask Tanmay to post it in the chat now.
He already posted it. Again,
no,
please.
But, because it will be there, scrolled up.
Right. Tanmay, just post it again once.
Yes, I'll keep it posting.
Yeah, and we'll do that again in the end once. That's
right.
Yeah.
That helps. Yeah.
And
yes, Abhishek, you have a question?
Yeah, I just wanted to ask small thing. Like most of the time we are solving in the, I think for pre-growth problems. So is there some kind of load balancing?
We'll be having that. We will be having that in the future releases. Load balancing is a feature we'll be adding. Presently, these are block parallelization, so slab and block parallelization. So